So for today, we are going to be talking about open loop op-amp circuits. So I was asked this question on Friday. I explained it briefly. We're going to go into a little bit more detail. We're going to talk about what specifically I mean by an open loop configuration. Okay. So for an open loop configuration, it means that we do not have a feedback loop. So our circuit is going to be something like this. An input can be applied to one or both of our inputs, and we will measure the output directly at the output terminal of our op-amp. And I've chosen to explicitly show the fact that our supply voltages also matter because of the saturation distortion that we covered at the end of Friday's class meeting. So an open loop configuration is what we've been dealing with up to this point. We're going to continue talking about it more formally today. Next thing that we're going to see is positive feedback. So in a positive feedback configuration, we're going to have our op-amp. We are also going to have, I'm not giving myself a whole hell of a lot of room here, so I apologize for that. Something like this. Where we're going to apply an input voltage. It technically could be, let me just put Vn plus here and Vn minus here. So we might apply our input voltage at the left-hand leg of that generic circuit element. But the main part of positive feedback is that we have a feedback path from the output of our amplifier back to the non-inverting input terminal. Okay. Negative feedback is effectively going to be the exact same thing, except that our feedback path is going to go to the inverting input terminal. So plus minus VCC plus, VCC minus, Vn plus. Here's V out. Here's Vn minus, right? So this is what negative feedback looks like. And the overwhelming, actually, let me rephrase that. All of the problems that we dealt with in circuits 1 were of the negative feedback variety, where we got to apply ideal op-amp rules. And by this Friday, we should understand where those rules came from and why we were allowed to use them. But until then, we're using our practical op-amp model that we developed in Friday's class. All right, so at the end of Friday's class, we talked about how the amplifier that we were dealing with in open loop configuration had an extremely small linear range, right? So for an amplifier with an open loop gain of 100,000 and supply voltages of plus and minus 10 volts, we saw that our linear range was only negative 100 microvolts to positive 100 microvolts, meaning that overwhelmingly the device wasn't actually operating as an amplifier. It would simply, or excuse me, its output would saturate to either VCC plus or VCC minus. So today we're going to talk about a particular type of practical circuit where this is exactly the response that we want, and it's called a comparator. Okay. So a comparator are op-amp circuits used to compare the strength of voltage signals against a particular voltage reference. So let's start by looking at this circuit. So I've got my op amp, I'm powering it. I'm going to apply my input voltage to the non-inverting input terminal. And I'm going to apply my reference voltage to the inverting input terminal. And I'm going to measure my output. Just for the sake of argument, let's say that our reference voltage Vref is 3 volts. The input resistance of our op amp is 1 mega ohm. The output resistance is 10 ohms. And the open loop voltage gain is 100,000 volts per volt. I want us to figure out what the output is going to look like if, actually, let me define a couple other things. So let's say that VCC plus is equal to positive 10 volts, VCC minus is equal to negative 10 volts. And then we're going to let Vn range from 0 is less than Vn is less than 10 volts. So I'm going to draw my practical op-amp model. So this is my V plus pin. Here's my input resistance of 1 mega ohm. Here's my V minus pin. As per usual, my differential voltage VD is defined as the potential difference between V plus and V minus. Over here, I have effectively my output stage. So this is going to be 10 to the 5 times whatever VD is. Here's my output resistance of 10 ohms. Here is my reference. All right, so this is my practical op-amp model. Now I'm going to connect all the other things, right? So my input voltage is between the non-inverting input and ground. So I'm just going to put a generic voltage source here and call it Vn. My reference voltage of 3 volts is connected between the inverting input terminal and ground. So that's going to look like a 3 volt source right here. And then my output voltage is measured across the output terminal and ground, like so. So mathematically speaking, our output voltage then, V out, is going to be 10 to the 5 times Vn minus 3 volts, because Vn minus 3 volts is my differential voltage for this particular circuit. So if I were to plot this, it would look something like this, right? So here is V out measured in volts on this axis. This is V in measured in volts on this axis. And this is my reference voltage of 3 volts. So let's start with something easy. So let's say that V in were 0 volts. What would my output of this system be? I disagree. So negative 300,000. So 0 minus 3 is a negative 3 times 100,000. All right, so negative 300,000. Now, is negative 300,000 volts more negative than VCC minus? Yes. So what does that mean? Our output is going to saturate to VCC minus. So if I put this bit right here to be negative 10 volts and this guy right here to be positive 10 volts at this point of 0, our output voltage is negative 10. What if V out is negative 2 volts? Or excuse me, V in is negative 2 volts. Negative 100,000, which is more negative than VCC minus, so it saturates to negative 10 volts. All right. What about, I don't know, 2.99 volts? So 2.99, let me do the math here because I'm not 100% sure. So 10 to the 5 times 2.99 minus 3, negative 1,000 volts. Okay. Which would saturate to negative 10 volts. So still very, very close, but not quite at 3 volts. We are at saturated at VCC minus. So I'm just going to connect those dots. Okay. Now, what about at 3.01? I would argue that's going to be positive 1,000, which is more positive than 10. So it'll be just at positive 10. And then it should be at positive 10 for all voltages greater than that. Okay. So effectively what we have is something that looks like this. Now this slight slope that I've given this line is actually quite an exaggeration. Because the linear range of this amplifier is so small, we could figure out what it was based on the gain and the power supply voltages and all that kind of stuff. We should see it's going to be not quite vertical, but extraordinarily close to vertical transition from VCC minus up to VCC plus, centered around our reference voltage. So effectively, whenever our input voltage is less than our reference voltage, we saturate to VCC minus, and whenever our input voltage is greater than our reference voltage, we saturate to VCC plus. So this is the operation of a comparator. Our voltage is simply compared to our reference. If it's greater, the output swings high. If it's less, the output swings low. Okay. So I could write this as V out will be equal to VCC plus for V in greater than V reference and VCC minus for V in less than V reference. If we're very, very close to our reference voltage, and by that I mean within a few microvolts, we might see that our output is actually going to be somewhere here towards the middle, but that's not really where comparators live, right? We are just looking for signal strength. Walker. V ref. Reference voltage for both. Yes, sir.
So, when you just said it, but clarify, for VA, it's so close to the reference.
It has to be incredibly close.
What does that make? Wouldn't that equate? Wouldn't it make like 0?
It would make it 10 to the 5 times whatever VN minus 3 volts is. But I mean, it has to be within a few microvolts of the reference voltage to not saturate. Right? So one of the drawbacks of a comparator like this is if we have a noisy signal, right? So I'll show you this on LT Spice on Wednesday. We are going to look at this in LT Spice, but I don't want to put the noise and all that kind of stuff in there until I'm ready to talk about it. But for a simple open loop comparator like this, if you have a signal with noise on it and it passes through that reference voltage, you're going to see it swing wildly from VCC plus to VCC minus and back around. We're actually going to talk about how we use positive feedback to fix that behavior on Wednesday. But before we do that, let's see what happens if we were to switch the pin that we applied our input voltage to. So this guy right here is what was called a non-inverting comparator. And this is how it behaves, where we largely ignore behavior around the reference voltage. Again, our linear range is so small, we are assuming that it's just going to saturate to VCC plus or VCC minus. Now, let's look at this guy. So here's VCC plus, here's VCC minus. Let's apply our reference voltage to the non-inverting input pin, our input voltage to the inverting input pin, and measure our output voltage. So I'm not going to waste our time redrawing this entire circuit, because if we look at this circuit, it's literally the exact same thing, except that these two voltage sources are swapped, right? So our output voltage would literally be just this, except that it'll be 3 volts minus VN, because VD would be our reference voltage minus our input voltage, right? What do you think that's going to do to our graph? Yeah, literally just flip it over. So for a non-inverting comparator, it had this shape. For an inverting comparator, it would be this. It's literally the exact same graph, but just flipped over the horizontal axis. Okay. So that we could say our output voltage as a function of input voltage is going to be VCC plus for VN less than V reference, and VCC minus for VN greater than V reference. So what I'm going to do now is I'm going to get on LT Spice and I'm going to implement one of these circuits. As soon as I figure out what happened to LT Spice, I thought I had it opened earlier, but maybe not. All right, so the first thing that I'm going to put down is my op amp. I use universal op amp 2 for all of my generic op amps. Okay? So you can see here we have universal op amp 1, 2, 3, 3A, 3B, and 4. Universal op amp 2 is effectively an ideal op amp, except that it takes into account our supply voltages to give us the saturation distortion that we need. All of them are configurable, so we can edit parameters like input resistance, output resistance, open loop gain, gain bandwidth product, slew rate, a whole bunch of other stuff that doesn't make any sense to you guys, and half of it doesn't make any sense to me. But we're going to stick with universal op amp 2 for the intents and purposes of this class. So I'm dropping this guy right here in the middle. One thing that I do want to point out is that the positive supply voltage is this guy labeled with a plus, and it's on the same side as the inverting input terminal. Could not tell you why it's set up this way in LT Spice, but it is. So make sure you're putting the positive supply voltage on the plus sign, the negative supply voltage on the minus sign. And if you're putting your signal on your inverting input, it goes here, and non-inverting input, it goes here. So it just looks a little wonky. All right. So I'm going to give myself some stubs of wire here. And then I'm going to move way over here to the left. And I'm going to set up my power supply. I'm going to do that with a voltage source. Give myself a little bit of space. And then a second voltage source. And I'm going to tie these two voltage sources in series. And then I'm going to give myself a little stub of wire out of that central point. And that's what I'm going to ground. So I'm setting up this voltage source for our supply voltages exactly like I set up the supply voltages for op amps physically when we were doing this in circuits 1. I'm putting my two voltage sources in series and then choosing my ground to be that midpoint so that I can get negative voltage and positive voltage at the same time. I'm going to choose 10 volts and I'm going to put 10 volts for both so that this point is 10 volts higher than this point. So this point down here is going to look like negative 10. You could, if you wanted to, rotate this voltage source twice, putting the positive polarity on bottom, and then just call it negative 10. But since most physical power supplies don't have access to negative 10 volts, I'm setting it up exactly like I would physically set it up in the lab. Okay. All right, so one thing that I want to show you guys, I'm going to put this label as VCC plus. I'm going to put it up here. So this node is now VCC plus, and then I'm also going to drop that label over here on the positive power supply terminal of my op-amp. So instead of physically connecting these 2 points with wires, I'm now telling this point to reference this voltage so that I get a cleaner schematic diagram over here in order to analyze and implement and all of that kind of good stuff. I'm going to do the same thing with VCC minus. So I'm defining it here, and then I'm referencing it over here. So now my supply voltages are set up. I'm going to create two more voltage sources. So one's going to be my reference, the other one's going to be my input voltage, and because I'm so close, I'm just going to move this stuff over a smidge. So I'm going to put my ground terminals at the bottom of each of these. Let's make V3 my input voltage. So I want my input voltage to go from 0 volts to 10 volts, right? Because that's how I defined it earlier. How am I going to set that up? There's a couple of different ways that we could do it. What I'm going to choose to do is to use a sinusoidal voltage and then just have it run for one cycle so that it will go from its minimum value to its maximum value. Okay. So I'm going to tell it to go for exactly one cycle. So a sinusoidal voltage usually goes from some negative magnitude to some positive magnitude, but I want it to go from 0 to 10. So to accomplish that, I'm going to give it a 5-volt DC offset. And then I'm going to give it an amplitude of 5 volts. So this should make it range from 0 all the way up to 10. For the frequency, I'm just arbitrarily going to make it 1 hertz. And none of this other stuff matters. So that's my input voltage. So I'm just going to label that guy Vin. And we're going to start by looking at a non-inverting. So I'm going to put my input voltage on the non-inverting input terminal. And then now I'm going to right click this guy and just make it 3 volts. This is my reference voltage. So I'm just going to label this as VREF. And lastly, I'm going to label my output node as Vout. So we have effectively drawn the exact circuit that I drew in LT Spice. So let's run our simulation. So this is going to be a transient thing. Realistically, I only need to run it for 1 second because I'm just doing 1 cycle at 1 hertz. Let's drop this down here, press the running man command, and I'm going to plot my input voltage, which is here in green. We can see that it is going from 5 all the way up to 10 and then down to 0 and back. Yes, Isaiah. 3 volts. I'm going to change the color of this so that you guys can see it a little better. Let's put it in blue. And then I'm going to have my output voltage here. I'm going to change the color of that and put it in red. So we can see that whenever my input voltage is higher than my reference voltage, and actually, let me throw something on here as well. That's too close to that blue. All right. So the blue line is my input, the purple line is my reference, and the red line is my output. So effectively, whenever my input voltage is above the purple line, my output is high. Whenever my input voltage is below the purple line, my output is low, which is exactly what we should expect. Now, this is a graph as a function of time. So it looks significantly different than what we had originally drawn. So I can actually fix that. If I mouse over this x-axis here and right-click, I can change the quantity that I'm plotting against. So right now I'm plotting against time. I'm going to change this to plot against the voltage V, open parentheses, Vn. And I'm going to delete Vn from the graph because I don't need Vn versus Vn. That's just a line with a slope of 1. And I also don't need my reference voltage here because it's already up there, effectively. So now I can see very explicitly my output is low until my input voltage hits 3 volts, at which point the output changes states and stays at VCC plus. Right? So this is how we get the exact graph that we plotted. Just as a heads up, I'm expecting graphs like this on your homework. Okay. For the inverting input, excuse me, the inverting comparator, all I need to do is just put the input voltage and the reference voltage on the correct place, right? So my input voltage should be here. My reference voltage should be down here. Rerun my simulation, and now it's swapped over, which is the inverting comparator response. So, do we have a good grasp on how these comparators work? Yes.
Can you grab an element move it?
So the move command is this hand. It's going to break everything. Yeah. All right. So yeah, so I reran the simulation to get this graph. To make it look like this specifically, I had to right click with my mouse around the x-axis and change my quantity plotted from time to V open parentheses Vn. So what I'm specifically saying is plot this as a function of the voltage at the node I labeled as Vn. Still not working? Let me see what you did.
Yep. Trying to keep up with you.
Holy God.
Yes.
You have tons of currents on there. So let's delete all the currents. So if there's an I in it at all.
I just clicked on everything at that point because I missed a few steps. I was trying to catch up with you. So
So the only thing that you don't have on here is the thing you need. You need the output voltage.
that's interesting.
Also measurable.
I think that's great in physics, right? I thought that we can have the same. But I did wrong.
You used the wrong type of op-amp.
Okay.
All right.
Thank you.
So what I want us to do now is design something. So I'm going to give you guys the design prompt. So what we're going to design here is a very simplistic analog to digital converter. Okay. So I want you to design a simple analog to digital converter, also known as an ADC, such that the output is equal to 5 volts, which is a digital high, when Vn is greater than 2 volts and Vout will be equal to 0 volts, or a digital low, when Vn is less than 2 volts. So a circuit like this will definitely be a comparator circuit because we are comparing our input signal to some arbitrary reference. So my first question to you guys is this going to be an inverting comparator or a non-inverting comparator? Non-inverting. Explain your answer, please. Yeah, so the output is high when Vn is greater than the reference. The output is low when Vn is less than the reference. So this would be a non-inverting comparator circuit. All right. So for a non-inverting comparator, we apply our input voltage to the non-inverting, right? Why are you with us thus far? By the way, our output always measured here at the output. All right. So what other things can we glean from this problem statement? What should my reference voltage be? 2 volts, because that's what I'm comparing my input signal to, right? So VREF is going to be 2 volts. And because it's a non-inverting comparator, we apply that reference voltage to the inverting input pin. All right. So what do my supply voltages need to be? 5 and 0. Which one's which? I mean, it's kind of obvious, but 5 volts has to be VCC plus. Put ground as our reference. Congratulations, you guys have just designed your first op-amp circuit. Just as a heads up, this is exactly how the analog to digital converter in your Arduinos works. So, five volts is a pretty standard voltage for digital circuits. 2 volts, not so much. So, how could we get 2 volts to use as a reference? So what I mean by this is, like, right now, we would need access to a 5-volt source and a 2-volt source. So that's 2 pieces of equipment that we would have access to physically implement something like this. I want to eliminate one of those power supplies. Okay. So how would I go about doing that? Walker.
There's 2 options. One, I would step up the voltage of some sort, 5-volt, that 10-volt to some sort.
So we're going to step something down from 5 to 2, because that's going to be a bit easier for us to do. That's not going to require a boost converter or anything like that. We're going to figure out how to do it with resistors. Okay. So effectively, we are going to have our highest point of potential in our system to be our positive power supply voltage. And then we're going to figure out our lowest point will be our negative supply voltage. And then we're going to figure out how to get something in the middle between those two using a resistor network. Okay. So that might look something like this. Okay. So this is going to be my VCC plus rail. So this one's going to be at 5 volts. This one's going to be at 0 volts or ground. I'm going to put my op amp here in the middle. And I've got it powered correctly. Here's my output. My input signal. That's going to change, so that's definitely going to require an external thing. But now I need to figure out how to get 2 volts at that node. Okay. Anybody have any thoughts? How I would split 5 volts to get 2 volts? I mean, it's going to take more than one. I told you it's with resistors. What kind of circuit should it be? Yeah, just a voltage divider. So design me a voltage divider that will give me a 2-volt drop from a 5-volt input. Holy God, why is it taking so long? Just 3 and 2. So if I put three here and 2 here, that's all I need to do. Now, I want to talk to you guys a little bit because I can't just use a 3 ohm resistor and a 2 ohm resistor. Or really I could, but I'm not going to. So we know that the internal input impedance of an op amp is on the order of mega ohms, right? So that means that in order to make sure that effectively no current branches off and flows into this inverting input terminal, I need to make sure that these resistors are significantly smaller than the input resistance of my op amp. So typically speaking, we bias op amp circuits using kilo-ohm size resistors because they're about 1,000 times smaller than the internal input resistance of the op amp. Okay. So 3 kilo-ohm here, 2 kilo-ohm here. Another reason we typically use kilo-ohm size resistors is to remind us that the output resistance of an op amp is usually on the order of tens of ohms to hundreds of ohms. So we need something small, or excuse me, larger than that output resistance so that there's not an appreciable voltage drop over the internal output resistance of the op amp. So the kilo-ohm size resistors is kind of the sweet spot for biasing any practical op amp circuit. So in this class, you will never see me use anything other than kilo-ohm scale resistors for any of the biasing because that's what we do in practice. Okay. So this circuit right here should function exactly the same as this guy right here does, except that we get our 2 volts using a resistor network as opposed to having a completely separate source provided to us. Really, that's about all I want to talk about for today. Yes. So I honestly don't know why that particular word is used. What we are attempting to do is establish a stable DC operating point for our system. And for whatever reason, I've never bothered to look up the etymology of it. We call that biasing the circuit. Well, all that means is just establishing, excuse me, a stable DC operating point. In your later courses, it'll still be referred to as biasing, but that stable DC operating point has a very special name called the Q point or the quiescent point. I also don't know why it's called that either, but that's the fancy name we give to the stable DC operating point. Yeah, unless anybody has any questions or wants to play around with LT Spice, see you guys on Wednesday for positive feedback. Yes, sir.
I was gonna ask you, where do you use to have sharing like paper on your iPad?
So I just found a PDF copy of a single sheet of engineering paper, and then I made a whole bunch of copies of it to make myself kind of like a pad. And then I'm using a program called PDF Annotator, which I think the version that I have is the last version before they went to a subscription-based model, which annoys the hell out of me because I can't put it on my other computers for free. So I think I paid like a one-time cost of around $40 for this, but that's better than hundreds of dollars for Adobe. There's got to be I figure I make enough money I can pay $40 one time. Right, so I understand that this pen right here is the 20 in parallel.
Yeah, I saw. basically, I thought online, this was certain project, certain. Some type of person. Basically, same particular.
So, specifically, we mentioned, that you might want to look at a process called delta Y curve information. It might be better for you from a getting point perspective to look up that and explain that. So effectively, you have
Are you asking about this? Yeah. Because I looked it up online, it's just like, weird. Plus I was doing my resistor combination, which is very like the wire there.
Right, so this is 10, 10, 10, 10, and 10. Let me get a different colored marker out. So I'm going to call this node X. This guy right here, Y. And this guy right here is Z. So
Is it just the bottom of that left box there? Or is it that whole node there?
I mean, realistically, the whole node, but when I do my transformation, I'm just going to impact that part right there, right? So what we will find is that to go from this delta connection to a Y connection, we are going to replace this network with,
Well, I'm gonna ask you about this.
so here's X. We'll have a resistor that we need to determine. This is a neutral point. A resistor that we need to determine. Here's Y. Here's a resistor. And effectively this point right here is V, and then we just have this other thing connected, right? Where we have a 10 here. A 10 here. And we're finding the resistance between these points. But now we have this thing in series. These two are in series. They can be combined. They're just in series with whatever that is. So when you have three identical resistors, it's actually just the resistance divided by 3 to go from a delta configuration to a Y configuration. So this is going to look like 10 thirds, 10 thirds, 10 thirds. So we're going to have 10 thirds plus 10 is going to look like 40 over 3 plus 40 over 3, or excuse me, in parallel with 40 over 3 looks like 20 over 3. 20 over 3 plus 10 over 3 looks like 30 over 3 or 10.
It's called delta Y.
Yes, so we went from a delta configuration to a Y configuration. It's also called a pi to T. So this kind of looks like the Greek letter pi, and this looks like capital T. We're going to do it several times, especially when we get to three-phase circuits. Troy, what?
I just want to make sure that this is how it's supposed to go. I was trying to catch up, but I still didn't know that. At least like what this is supposed to look like.
That looks like V out as a function of time. But what does V in look like? Because I'm not 100% sure that I.
Which part?
All right, so this is for an inverting comparator. So whenever your output is less than your reference voltage, whenever your Input is less than your reference, your output goes up. Okay, so the graphs that I'm looking for on homework or whatever, let me. Yes. Actually,
Wait, how did you get that? You just clicked on VN?
yeah,
Okay.
so to put that curve there, I don't want to delete that, I just. There we go. Click on VN and it puts my input curve on there and all. For your homework, so right now, this is V out as a function of time. And I can tell that this is a function of time because it says seconds.
Yes, sir.
I don't want it as a function of time, I want it as a function of VN. So I right click down here and I change my quantity plotted from time to the voltage at node VN. Yeah, and so now this is V out on the Y axis, VN on the X axis.
And this is like what you go.
Yep.
Okay.
Absolutely, and it's exactly how we drew it in class too.
Okay. So this is right though, for this, all right.
Yeah.
Perfect. Okay, well, thank you. That's all I had.
Who's next? Sure.
I got it.
30 pages. All right. I mean, I'm using the show you how to do it with 31, so.
Oh, yeah, well. I think offered it isn't 15.
Oh, that's gonna be annoying. Just to be clear, you don't have to hand write out the problem statements. You can copy and paste that stuff if you want to. I think I had mentioned that. Yeah, so that'll save you 20 minutes per problem, especially with some of these older ones. Mesh, okay. Use Pascal's method. Yep, yep. Use MathCAD, fantastic. Yep, so if you did problem one like that, you can do all the rest that way, perfect.
So, okay. It is self-employed. And I'm probably going to, my telemetry.
So you chose to reconfigure the 10
Yes.
and moved it into a delta. So to go from a delta to a Y, you divide by 3. To go from a Y to a delta, you multiply by 3. So that should be 30.
30,
Yeah.
Okay.
Also, how to move it, take it as a delta, and then solve the Y.
Yep. So let's look at this thing now, right? So down here, you have 30 in parallel with 10. So that's going to be 300 over 40. In series with 300 over 40.
In series.
2 and 15. In parallel with another 30. That's
Right? 15 times 30 over 45. Figure it out.
okay. Thank you so much.
Yep.
I was struggling with the values. I did not know yet to do some math to change the values.
Yep. You can't just make them the same thing. That's not how. Cameron, or do you?
Yeah, I was just gonna ask, are you gonna be posting?
No, I uploaded the videos, but I forgot to put the pages or whatever on Canvas. So the first 2 videos are actually on YouTube. I just need to give you guys access to them. They'll take me like 5 minutes. I'm sorry, I just slipped my mind this weekend. Cameron, what else?
Format for the graphs. I didn't, because I didn't even want to think out the video. But now I changed the concept with EBM.
All right, so first I'm gonna get rid of these parents because I don't understand why they're on here.
On the like right of
And you don't need the in on, so it shouldn't be VN versus VN because that should just be aligned with the slope of 1. So I am mildly concerned. So I think one big issue is that You don't have these guys grounded. And so it doesn't know what it's putting them with respect to. Well, it's that. There we go. That's it. That's it.
Our reference. This would be, go ahead.
This is a non-inverting, right? Because your input is on the non-inverting terminal and your reference is on the inverting. Yeah, that's right.
Converting it, that would be.
Yeah, so if you swap those two voltages, then it would go, it'd be high, then switch to low.
And for the homework too, it's gonna look like a low. Not exactly like this, it's gonna be
Similar.
high and low.
Yep.
We just have to do the amplitude of the times. Yes, you change the voltage. Or.
I don't know what you're talking about. Oh, so for this one, I literally just want you, so this stuff is gonna be for homework that moves. Okay. This thing right here, is a gain of 12.
Yeah, right.
So make this exact curve 12 times 1. That's it, for part A. Because, so this peak value of 1.5, what's 1.5 times 12? Yep, okay, so it is 18 less than positive 20 volts. All right, and then we have a peak negative value of negative 1.5. So is negative 18 less negative than negative 20? It is not. So it's literally just gonna be this exact curve, but scaled by a factor of 12. For part C, then I start screwing with the supply voltages, which is you're gonna see things are gonna cut off and saturate on VCC plus and VCC minus. So it's literally just gonna be this curve, except parts of it are gonna be slashed off the top and bottom of it.
Oh, so we just, it's a cutoff right there. Whatever voltage is.
Yep, and then we'll cut off down here at whatever a voltage appropriate. And then for part C, you're just telling me what those cutoff points and all that kind of stuff are. Part D is the exact same thing, except a different set of supply voltages. Part D is the same shit as part C. Okay.
I've done the math yet, but is the math yet just verifying the math with the.
Yeah, and if you don't have to verify the math with MathCAD, you don't need to verify the math with
God,
MathCAD.
that's true. I already finished it. I think it's a good math yet. You want to go up to this.
MathCAD isn't required unless I specifically say, using MathCAD, do something.
But it's a mighty useful tool to do five, just real quick, five.
For sure.
So this should be. That's why. Or as of right now, your homework, Friday is so nice.
I'm seeing an incredulous look behind you.
I wouldn't say it's a.
I mean,
Nicest thing ever, but-
I smoked for 5 days.
You get to rerun.
I believe it was 5 days.
I signed out on Monday, it's due on a Friday, something like that. 4 days, whatever.
Well, follow with it.
What are you trying to solve for? Yeah. So, yeah, so I1 is equal to 0.1 IY. And then IY is I2 minus I3. And then you'll do a KVL equation around this one, KVL equation around that one. And then that's not your Norton current, that is your test current. But that's just gonna be negative I3.
And find my Norton, I'll just do.
You're not finding
Where does it go? Sorry.
you're not finding I Norton because there's no independent sources here. So Norton means specifically short those terminals, find the current flowing through the short. Well, if you short those terminals, you're gonna get 0 for everything because there's no independent sources in here. So you're finding the test current. So you have everything set up right, that's just labeled. Yeah.
Because I don't know where short this voltage.
Yep.
Okay, my bad.
Yep.
Cool, so I would just take that retest by the.
Exactly.
Sweet, that's literally what we're doing.
Yeah.
So thank you.
Well,
So this would, if I do this. Probably 35.
Yeah.
Now,
I4 would be able to I Norton, yeah.
so I didn't know on the previous
for the problem,
Seems reasonable.
and I thought that y'all were saying that short. Then, this can only occur with the gap. So the bubble is the line. So
18 is what the one that's saturation, the one that is saturated. Only thing for this one.
Did you resolve for all of your nodal voltages? No, but those are for part A. So what I'm saying is you would have to completely reach, exactly right.
Okay.
Yeah, you can't use those previous values because that short wasn't there earlier.
I thought I was losing my mind.
Nope. So, a simple mistake, I've seen it several times. That's why I was like, wait a second. Yeah. So what other transformations are there? Oh, God, there's so many. We'll get into like network theory and all that kind of stuff. Yeah. Okay. Yeah. There's a lot.
All right, we're back with another graphing question.
Okay.
So we typed in our numbers for the first problem on the homework.
Okay.
Is this like correct?
I don't know. What's the first?
For part A?
Homework set number 2 is for what we did on Friday.
Oh, this is. gonna
This
be
is
for
homework 3.
Oh,
Okay,
so
yeah,
you want
okay.
us to plot it like this on the two?
Yes. So
Oh, okay.
literally, you take this graph,
Yeah.
scale it by a factor of 12. Like part A.
Okay.
So I say that because what's your peak value of your voltage here? 1.5 volts.
Yeah.
It's 1.5 times 12. 18. Okay, is 18 less than VCC plus? Okay, so there's not gonna be any saturation distortion.
Okay.
What is negative 1.5 times 12? Negative 18. Is that more negative than negative 20 volts? It is not. No saturation distortion. So it's literally gonna be this exact graph, except where it says 1.5,
Yeah.
make it say 18.
Okay.
Part B, now I'm screwing around with the supply voltages.
Mhm.
So now you are going to have saturation
Yeah.
distortion. So you're gonna see that parts of things get cut off. Part C is just figuring out what the linear range is and then where it saturates. Part B is the exact same thing as part B, except that it's a different set of supply voltages.
Okay.
Have you started on problem 2 yet?
Yeah, I think, yeah, I think I did.
Okay, so I just want to be clear here, you actually have an output
Yeah.
voltage or an output resistance. So the best way to take that into account is to effectively just treat your output stage as a voltage divider. So instead of just having output is AVOL times VD, it's now going to be AVOL times VD times RL over RL plus RL.
Mhm.
And then if it's more positive than VCC plus, it saturates to VCC plus. If it's more negative than VCC minus, it saturates to VCC minus. E is obviously the only one that saturates.
All right, thank you. Thank
Yep.
We do have to use, draw the practical circuit.
Yeah, I mean, you could probably figure it out without it, but it will make a lot more sense. Actually, you should get in the habit of drawing.
Yeah.
Well,
We never use the ideal.
well, we're gonna learn when and why we can use it first.
There are a set of information.
One of the main conditions is negative feedback. If we don't have negative feedback, we cannot use it. Okay.
Yeah, I just like the, that's sense to how much money. Yeah, no reasons. Oh, you can go. I don't know, I heard you explain to them. Problem one, but.
All right. So the answer is the answer for which part?
From one, it's just graphics.
Yeah.
Like 18.
Okay, so the peak value of the input voltage is 1.5 volts,
That's a fire.
right? Because that says 1.5 and that's the maximum.
Where'd you get the?
Because I'm trying to figure out whether or not saturation distortion will be a thing. So if it's below the peak value, that's less likely to cause it to saturate. Same thing for those negative. Yeah, exactly right. So my voltage gain is defined to be 12. AV is equal to 12. So what's 1.5 times 12? 18. 18 less than VCC plus. that I'm not gonna have saturation distortion for positive voltages. Is negative 1.5 times 12 more negative than negative 20? It is not, because it's just negative 18. So for part A, it's literally this exact graph, except that it hits its, the out, it hits its maximum value at plus 18 and its minimum at negative 18. So literally redraw this graph and change the state.
Would it still be the bottom?
Yeah. For part B, it's the exact same thing, except now we have different supply voltage. So we are going to have saturation distortion. So let me. Something like this, right? 18. Negative 18. So this is the answer to part A. So what's VCC plots for part B? Okay, all right, the 10 is somewhere around here. Which means this part's gonna get chopped off. This part's gonna get chopped off. What's VCC minus?
When I graduated,
That part's gonna get chopped off. That's the answer to part B. Part D, different supply voltages, different parts get chopped off. That's it.
And,
Did I ask the question poorly?
no, it's just, well, whenever you said, based on the input waveform shown below, I just don't know how to treat that.
Yeah. So I gave you VN, I gave you the voltage gain, and I asked you to be. Yeah. AD times V. That's it.
And, yeah. I don't know where to get started on part two.
Then draw your circuit as a practical office. Right? So
have you been looking at internet? No, I've been looking one page. I should have just done it. Do you put enter after it? Is it working out?
here's the load resistance, here's the output resistance.
Some is good fresh.
Here's input resistance. Well, here's the plus, here's the minus. Right? So V out is going to be AVOL times VD, where VD is just V plus minus V minus. And then I have a voltage divider here at the output, so that's gonna look like RL over R out plus RL. Plug in the numbers that I give you for all 5. That's it.
Do V plus and V minus work?
Doesn't matter. I mean, if you, okay. Oh, shit. So now I'm gonna change VG to be V2 minus V.
What would we actually? I wasn't about to leave them, but if you're saying, well, I'm probably.
So VD is always gonna be V2 minus V1. Oh, I forgot to label that as V1. My bad.
And for
The voltage here is always gonna be AVOL times VD. And then this voltage drop is being divided between R out in series with RL. So I just use the voltage divider related to figure out just the portion over R. Then
It's like
plug numbers in. If this is greater than VCC plus, it saturates VCC plus. If it's more negative than VCC minus, it saturates VCC.
So that's why every time I say that, I think it's.
Yep.
Anytime I tell myself something that's sensitive.
Yeah. Sure. I don't. I didn't even know. I did it with ABL.
That's gonna put VX between this node and this node.
I have.
Oh.
It was originally between this node with terminal A and this node at the top left of the circuit, so it's still between those two nodes. So VX isn't really the voltage drop across the 10 ohm resistor, although it is, it's the potential difference between these 2 points, between these two nodes. So it still needs to be between those two nodes if we were to do a source transformation.
Oh, so it wouldn't be.
Right, but if you put VX to be between here and here, it's very obvious to see that VX is negative 30.
Right. I did that, and I was being positive very nice.
It is serious. I set one on.
Where's the-
It's a long piece. Takes your long. It gets on your phone.
So VTA, can I write this down?
Yeah.
So I'm gonna do KVL around it in this direction. Okay, so negative 2VX.
But okay, but here's the thing, when people call me, like I've had people call me 50 times. Like,
Nothing there because it's not part of the closed current carrying circuit. Minus 30 volts plus VTA is equal to 0, right? So I have one equation of 200. So VX is gonna be between here and here, so VX is negative 30.
I put it to the.
So VTH will be equal to 30 volts
And then you're like tomorrow, like on Tuesday and Thursday, it's I have.
Plus 2 times negative 30 volts
I mean, I'm not gonna,
is negative 30 volts.
I woke up today,
So-
I'm not gonna sleep.
So with any resistor, even if it's
I don't
open
sleep
loop,
anyway.
even if it's between two voltage sources, you still know. Like you still wouldn't include the 20 ohm or.
The 20 ohm right there, how much current flowing through the 20 ohm resistor? There's no closed current carrying.
Oh.
Right, so the current is 0, the voltage drop is 0 across the side, the voltage drop is 0.
So for the open loop 7, you just want to do the voltage. But also for the source transmission, does it matter if you put the voltage source on this side and the resistor on this side?
Not at all.
Okay.
But I want to be really clear here, let me get a different color. Right? So. Originally, VX is defined between here and here. So VX will still be defined between those two nodes. So this is the VX that you have, which is going to happen to be negative 30 because we know there's no drop over that 10. If you only put the VX as the drop over the 10 ohm resistor, that's why you were getting 30 volts. Because let's see, the VX was 0, 0, 0. Don't come out, anyway, if you're going to do the source transformation, make sure you're very meticulous about making sure that the voltage VX is defined between the same pair of nodes as it was defined originally.
Because this would give you a 30 voltage source, but because VX had positive over here, I originally wrote like just this combination, the positive would be over here, but because VX was like swapped it.
Okay,
I
so now,
changed the sign.
okay.
Because I didn't know how to do that. So I thought like whichever way the current source is playing, that's the cycle for the logic on.
It should be.
Right.
And 3 times 10, so it should be positive 30. So I'm not.
Oh, yeah, because, yeah, it is. Wow.
But Vx is still gonna wind up being negative 30 because it's the opposite polarity. It's the same voltage, but opposite
Right,
polarity.
yeah. Okay.
Yeah, so it should be a positive 30 volts there after doing the source transformation. Because if the head of the arrow is on the right, the positive sign is on the right. The tail of the is on the left, or negative is on the left. It's a positive 30 there. KVL around the loop, negative 2 Vx.
But it's because VX, the positive terminal of VX is over here, that VX would be the negative.
Right. Okay. Because, yeah, so the positive polarity terminal of Vx is on the negative polarity terminal of the 30-volt source. The negative polarity terminal of Vx is effectively the positive polarity terminal of the source because there's no current flowing through that resistor. There's no voltage.
Okay.
And then you'll still get negative things.
Okay. I was just explaining one, right? I never seen it.
Yeah. So I was expecting you guys to Google it and all that kind of stuff, but it's fine. So when there are 3 resistances and they're equal to each other, to go from this delta configuration to a Y configuration, you simply divide the resistor value by 3. Okay. So that's why these 10s look like 10 thirds. So effectively what I'm doing is I've subdivided this network, excuse me, in between these terminals X, Y, and Z, and I'm replacing it with an electrically equivalent network between X, Y, and Z. And then you get this. Now, let me show you something slightly different before I have to go to my next class. We could have just as easily said, with this X, Y, and Z. So now we have a Y network and we might want to replace it with a delta. So here's our original thing. So here's our 10. This is terminal X. I'm just going to leave this crap blank. Here's terminal Z. Here's Y. Here's a 10 over here. So to go from a Y to a delta, because all of the resistors are equal, we'll multiply by 3. So that means we're going to have 30, 30, and a 30. This 30 and this 10 are in parallel, right? So over here, let's see, 30 times 10 is going to be 300 over 40. Right, 30 times 10 over 30 plus 10. Same thing down here. Add those two together, 600 over 40, right? What's 600 over 40? 15. Right, because 600 over 400 is 1.5, yeah. So 15 in parallel with 30 is 10. So regardless of which transformation you choose to do, whether it's a delta to a Y or a Y to a delta, you're going to get the exact same result. So it doesn't matter which set of resistors you choose to transform, it's going to work out either way.
So you just do a transformation, make it easier to get resistance.
Well, as it's drawn like this, other than doing a transformation, the only other way to do it would be to do test source or something like that.